Since we have got all our forces of the components in the x and y directions, and I've chosen my x directions to be down the incline, we can proceed now to write down the equations of motion of the block. As you can see, as I am doing problems here on physics, we are coming to more and more complicated cases involving a number of forces. We need to draw them, resolve them, write equations of motion. But if you have your basic fundamentals correct, in such case, you should not be daunted by the number of forces. The same principle applies, and you could write down the equations of motion cautiously, not missing any force on the body under investigation. So here we go and write. Look here, in the x direction, taken to be downward in this figure, as you can see, I took it down the incline to be positive, so my positive force is mg sine theta. That is the force acting in the plus x direction as per my assumption. And here we have got two forces, F cos alpha and small f, frictional force. Both of them are acting up the incline, so they are in the minus x direction. So we write minus F cos alpha minus frictional force. Now this is of course static frictional force, because you understand that since the block is kept at rest, it is not sliding down or sliding up, this must be static frictional force. So this is minus Fs, and of course the block while at rest, acceleration is 0, and that's my equation number 1 for x motion of the block. Before I write the equation of y motion of the block, let me take your attention to this figure once again. I have just modified it very briefly. I want to make it very clear that this symbol means we are discussing the situation where the block tends to move downwards, but we are applying a force to resist any such motion so that acceleration becomes 0. The block doesn't move down, but the tendency of the block is to move down. Hence we have added this red arrow here to denote that. Now let's come back to write down the equation for y motion of the block. This is Fy, and as you can see, according to my choice of plus y axis, n and f sine alpha are positive and mg cos theta is negative. So we go forwards and write down the equation of y motion. That's coming out to be n. As you can look at the figure and corroborate what I am writing, n plus f sine alpha, they are positive y direction, and the only force acting in the minus y direction is mg cos theta. And once again, the block does not leave the surface of this inclined plane, so there is no y motion here. And once again, I could write down this is coming out to be 0. That's my equation number 2, equation for y motion of the block. So from here, I can proceed to write down from the equation number 2, I can proceed to find out, this is equation number 2, and I can show that the normal force that is acting onto the block is given by mg cos theta minus f sine alpha, and in the limiting case, this is the limiting case here, when the block is just about to slide down, in that case the static frictional force becomes equal to the limiting frictional force, that is Fs max, which by the law of static friction is given by coefficient of static friction mu s into the normal force, and that is coming out to be mu s. I put the value of n just now obtained, that is mg cos theta minus f sine alpha. Remember, this is the value of static frictional force when the block is on the verge of motion down the incline. We shall put this value of Fs max in my equation number 1 and see what is the lower limit of the applied force F. So going back to equation number 1, I could write down, this is mg sine theta minus f cos alpha, and just now I have shown that when you go for the lower limit of the applied force F, we must consider the situation where the block is on the verge of motion down the incline. Hence, static frictional force becomes equal to the limiting frictional force, and we just replace this value of Fs in this expression and get that it's coming out to be mu s, and in bracket mg cos theta minus f sin alpha is equal to 0. Now proceed from here, this last equation. As I can see, if you open the bracket, I am getting f cos alpha here and one more term involving f, that is f into mu s sin alpha. Be careful about it. Bring f onto the one side, take other terms to the other side, and show eventually, this is the work left for you, that you show that f min, that is the minimum value of the force to be applied so that the block does not slide down the inclined plane, is found to be mg, then inside bracket sin theta minus mu s into cos theta, and the whole thing divided by cos alpha minus mu s sin alpha. This is the result you must get. Once again, you should be able to show from this last step that f value is coming out to be mg sin theta minus mu s cos theta by cos alpha minus mu s sin alpha, where of course you can look at the figure. Theta was the inclination of the inclined plane and alpha was the inclination of the applied force F with the inclined plane. So these two things have to keep in mind. Mu s is the static frictional coefficient between the block and the inclined plane, and this is the minimum value because, as I have explained here, if the force is less than this value, the block would slide down under the component mg sin theta. So this is the minimum value. You must come to this result here. So we have highlighted our latest finding that gives the minimum value of the applied force. Call it equation number 2, keeps inside a red box. And it is a time for us to introduce what the result we got at the beginning of this lecture. That was the angle of repose and numbered equation number 1. So I had promised that time that this result we can incorporate in my result to get something very interesting. It's a work for you once again. You replace this mu s in the expressions here and here by making use of equation number 1. Mu s is tan theta s, where theta is of course is the angle of repose between the block and the inclined plane. Proceed using your knowledge of trigonometry and show that the minimum applied force can be written more compactly, more attractively as mg sin theta minus theta s divided by cos alpha plus theta s. Here you must understand theta is the inclination of the inclined plane that we discussed in this problem. Theta s is the lower value of theta at which the block is just about to move down under its own weight only. That is called angle of repose. We have done it before and reminded you at the beginning of this class. Alpha is the angle made by the applied force F with the upward inclined plane, that is alpha here. And if you could make use of this mu s is equal to tan theta s, then you could express the same result in a much more compact and attractive form as we have shown here. Prove this result also. This is a work for you again.
Hello students, you got a glimpse of our video lessons through this small lecture. We have hundreds of lectures like this one covering various topics of advanced school level and intermediate physics in our website. They are exhaustive and often accompanied by elaborate diagrams to make concepts even clearer. They are taught with passion and sometimes with a bit of fun. So, at the end of the lesson, you have a commanding grip on the subject and you are ready for the board and competitive exams. Subscribe at physicsacademyonline.com to access video lectures of highest standard on various topics of physics.